Hi, this is Sylvia and welcome back to my videos. Michael Scott just posted a really quick video that I thought I would scribble on just to make it a little bit more clear. So let's go to his video where he's talking about the OpenSees transformation. And
the orange vector is local z, right? The green is local y, okay?
So what does that mean? The local x-axis is always defined going from node I to node j. So there's our local x-axis. What he's showing here in the orange, on the other hand, is the local, let's say that is your actual z-axis, okay? It's a local z-axis. But it's actually, let's call it z prime, because this is what you put into OpenSees to define the local z-axis. But what the program will do, it will take this z-axis that you give it. It could be any vector in this plane, as he shows. So I'm going to play forward here. Okay, and he's going to spin this z vector here.
Sees wants is some vector that lies within this xz plane. Any vector, really, in the xz plane, except for x itself. Right?
Any vector, really, but if you notice the local y-axis, which is this green vector here, this green vector never changes. No matter how much he spins this plane, so these guys are in a plane, no matter what he does, this local y-axis doesn't change. Okay, so watch. Maybe I'll go back a little bit.
Sees wants is some vector that lies within this xz plane. Any vector, really, in the xz plane, except for x itself. Right?
So your local x-axis is actually in this direction, which means that this is node I over there and this is node J. Okay, so if this is your local x-axis and this is your local z-axis, or any sort of, call it z prime, because it doesn't have to be exactly that. What OpenSees is going to do is it's going to take the cross product of your z prime and your x vector. And so z cross x gives you y. So it takes the cross product and it creates this local y-axis. Then it's going to take the x cross y and compute the actual local z-axis that is going to be perpendicular to all three of these vectors. And so here you could see the orange line doesn't have to be exactly parallel to your local z-axis, but the program will compute it. And so it's just a really nice way of, when you've got things at an angle, there's always some axes that make sense. And so it's not as daunting, as scary as you think. What I want to do is I want to open up the program and actually shows you that it's doing that. So I'm going to keep this, and if I go to OpenSees GitHub, and then I think I search, if I search for transformation, here it is, get local axes. So this is in the linear coordinate transformation in 3D. You can see here that it defines the axes and the vector, the x-axis, it takes from node I to j. Compute y as v cross x, where v is stored and it gets sent in, okay, for the local z-axis. So here it is, it computes the y-axis component by taking the cross product of the z with the x, okay? And then it normalizes, it's got the y-axis, and now it computes z from x cross y, and now you have the local z-axis. Okay? And so that's how it does it in OpenSees. In summary, the program computes this local x-axis going from node I to j. Keep that in mind. So it's really important if the directions of your local y and z axes are important. If you have a section that's not symmetric in the two directions, always make sure that you're dealing with an x axes going from I to j. So I always go from left to right, bottom to top when I define my ij nodes in my element. So the element defines x. You as a user define some sort of little vector here that is in the plane. So it doesn't even have to be orthogonal to x. Then the computer is going to take the cross product, compute the local y, and then so these are right angles, and then it's going to take the cross product of those two and compute the local z. And that's it.